So, what are we going to be making today? We're going to be making one of these custom city maps, and perhaps you're like me and you've stumbled upon one of these like custom city map prints online. What you can do here is basically enter a city, zoom in, zoom out as much as you want. Pick a color palette. Maybe you change the color of the background. And in order to get a digital download, I have to pay at least 21 Canadian dollars. And that's just for like a digital download. I don't even get a physical print. So I asked myself, like, is there a way to do this for cheaper? And yes, it is possible using open source tools like R and OpenStreetMap. So that's what we're going to try recreating today. Okay, so I name dropped OpenStreetMap. Maybe you've heard of it before, maybe you haven't. So what is it? Okay, so OpenStreetMap looks something like this. And you can access it by just Googling it, or it's openstreetmap.org. And what it is it's a map database that's built by a community of volunteers that contribute and maintain data about things like roads, trails, restaurants, cafes, and much more all over the world. So if I zoom in, you can see like we're here today. It's been labeled as Invest Ottawa. And the data, or OpenStreetMaps, it provides data for thousands of websites and mobile apps like Pokemon Go, Snapchat, and Uber, just to name a few. And it's also used for other purposes like humanitarian aid and academic research. So we're going to be working with OpenStreetMap data today to recreate that city map. Now, how do we get our hands on OpenStreetMap data? What we're going to use today is the OSM data R package. And to like explain it at a very high level, OSM data, this package uses the Overpass API to retrieve the OpenStreetMap data. And essentially, as a user, what you're going to be doing today is sending queries to the Overpass API using this package. And then in return, you'll be receiving a portion of the OSM dataset that matches your request. Okay, so now we're going to go in and open up our studio. And I'm going to open up the Ottawa Map Starter QMD. Is this font too small?
I would zoom in a little bit.
A bit more? Okay. Is that a little better? A bit more? How's this? Good? Okay, cool. All right. Okay, so the first thing I'm gonna do is to press this green play button on this code chunk, or use the keyboard shortcut of your choice to run this code chunk to load the packages that we're going to be using today. Scroll down. Okay, and as a side note, you'll see that in many of these code chunks, I've already provided like a variable to get you going. I highly recommend that you continue using the provided variable names just so that you and I are able to stay on the same page throughout the course of this workshop. Okay. We talked about this idea of sending a query to the Overpass API. So how do we set this query up? All queries, from my understanding, start with defining what's called a bounding box. And this bounding box is basically the geographic area that you want to search within. So there's at least two different ways that you can do this. The first looks something like this. You don't have to copy this bit, but so the OPQ function lets you set up a query, and in it, I'm going to call the get BB, which I think stands for get bounding box. and then pass in a string representing a city or the area that I want to create a bounding box around. So if I do this, you'll see that it basically returns the latitude and longitude limits that correspond to the area name that you passed in. But there's also another way of setting up a bounding box, and that involves using coordinates directly. And we're going to be going with option B today. So basically, you can also manually specify the minimum and maximum latitude and longitude values if you want to like precisely define a bounding box. So just to show you how you can do that, on the OpenStreetMap website, you can hit export. And what's cool is if you click on manually select a different data, it'll give you this like box. And then if I move the box, you'll see that the numbers on the left-hand side under export change. So basically you can play around with this box to get the bounding box that you desire, and then copy and paste the numbers that show up in this gray box to define your bounding box. So that is basically how I chose the limits that I want to work with today. So I'm just going to go back to our code. Alrighty, give me 1 second. All right, so instead of using a string to define our bounding box, let's use a combination of longitude and latitude limits. So we're going to define our bounding box. I'm going to call that B box, and it's going to be a vector. Oh, and this bounding box that I specifically picked is the same is what I used to get that map that you see there. And it covers my areas of interest, which are places like the Bayreuth Market, Glebe, and Little Italy, just for context. Okay, so my X-min is going to be negative 75.731. For your reference, that's going to be your westernmost extent. And no need to copy the code comments. That's just for me to explain to you what's going on here. I'm going to set my Y min to 45.399. I'm going to, sorry, and then that is my southern most extent. And then my X max, I'm going to set to negative 75.667. And that's my easternmost extent. And then my Y max, I'm going to set to 45.444. And that's going to be my northernmost extent. And once I've defined that vector, I'm going to run it. And when I call VBox, I should get something like that. And as I wait for you guys to type and get caught up, for this particular workshop, I like on purpose chose a relatively tight bounding box, since the more I would zoom out, or the more I zoom out, the more area I end up including, and that might return a lot more features, making the corresponding query computationally expensive. So just to kind of keep things lightweight, I'm narrowing in on a very small area here. And then for those who have defined bbox, what you can do next is to pass bbox into the OPQ function that we saw earlier to build our overpass query. And then when I run query, it has a couple different attributes, but in it, the bbox attribute should be the same as the bbox that you defined earlier. Any questions so far? Yes.
Okay, so if can I type like in the get BB function.
Yeah.
You put like Ottawa, Ontario, but can you do like, for example, I typed like University of Toronto. That didn't work. Does it have to be like cities?
I'm not sure. Like, I tried playing around it myself. Cities seem to work, neighborhoods seem to work, but I'm not sure if like a particular building or like an institute works. Yeah.
I know when I was looking at like the wiki data,
Yeah.
the like restaurants and like universities, so for like a sub.
Hi.
So maybe like like that was the thing I was thinking of.
Okay, so I'm just gonna continue blabbing, but I'll leave these two code chunks up here. So basically, when you're querying OpenStreetMap data, we don't want to be retrieving every possible feature within a given bounding box. So I mean things like every single light pole, every single stop sign, every single bus stop, because this would be way too resource intensive, right? So we basically just specify the features that we care about. And in the context of our map, it's things like where parks are, where water bodies are, where roads are. So once we have our query set up, there's other functions you can pass this query into to fine tune it basically. Okay, so is it okay if I move on? If I scroll down a little bit? Okay, I see no objections, so I'm gonna scroll down. All right. Yeah, okay. 1 second. So no need to copy this particular bit I am going to be typing out. This is just like to demonstrate a couple of concepts. After our initial OPQ call, as I said, like we can fine tune our query by adding one or more features to fine tune it. And we use a function called add OSM feature for this. 1 second, sorry. Why can't I? Why isn't my pipe shortcut working? There we go. Okay. So a feature can be specified at a high level using what's called a key. So I could do something like key equals amenity that I spelt incorrectly. And what this would do is return every single object like within my bounding box that has the key value amenity. If you want to be more specific, we can provide a key value pair. So instead of providing just key equals amenity, we could do something like key equals amenity, value equals healthcare, and then it's going to return objects or features that have these particular set of tags associated with it. So I assume maybe this might return something like clinics or like hospitals within your bounding box. That would be my guess. And you might be like, why are you throwing these terminology, like these terms like keys and values at me? Like, how am I supposed to know which keys and values to use? If you are asking that question, that's a good question because I wondered that too. And it turns out I think if you like Google OpenStreetMap key value dictionary or like map features, it should take you to this wiki page. And basically, it has all of the key value pairs that exist in OSM data listed for you, like a glossary. So if you are curious as to how OpenStreetMaps labels and categorizes the different things in the space around us, you can take a look at this glossary. But just note that like every tag that's listed here isn't necessarily going to appear in our bounding box, right? So, for example, yeah, so there's different keys like aerial way, boundary, building, emergency. So just for context, like this is where all the keys and values are coming from. Okay, so now that we understand key value pairs a little bit, let's start by retrieving water features that we want to include in our map. So just as a refresher, by that I mean the light blue stuff is what we're going to try to fetch first. Okay, so as a disclaimer. I've like in putting this workshop together, I noticed that Ottawa is a little tricky because we have several different types of bodies of water. So we have rivers, we have canals, we have lakes. So there's like a lot to like figure out, but we're gonna start with the major rivers running through the city. So that'd be like the Rideau River, Ottawa River, and I think a piece of the Gatineau River will end up on our map as well. All right, so going enough with the yapping, I'm gonna go back to my code. All right, so in this first code chunk under extract OMS data, I'm gonna begin with my query, and I'm gonna pass this into the add OSM feature function. And then to get the major rivers, the key I'm gonna use is natural, and the value I'm gonna use is water. And then once I've provided the key and value arguments into add OSM feature, then I'm gonna pipe this into OSM data underscore SF. And basically what the final step, the final function, what that's doing is that it's returning whatever the result of that is as an SF, a simple features object. And it's just the standard format in R that we use to store and represent spatial data. And once I have that pipe finished, I am going to store that in a variable called water underscore A. And then I am going to run it.
Yeah. Yeah, she just. Oh, yeah, she just got it.
Okay, I'm gonna try to leave this code chunk up. And I'm gonna explain what like this output looks like. So if I type water underscore A in my console, I see an output that looks something like this. So it looks like the returned object contains multiple components. We have things called OSM points, OSM lines, and OSM polygons, and also OSM multi-polygons. And basically, as we put our map together, and I guess in general, as you work with OSM data, you're going to need to select the components that corresponds to the geometry type that you're interested in. And what I mean by this, I have other slides for this. Give me a second. Okay, here we go. Okay, are you able to see that? Okay, so that is in your way. Okay, yeah, so point objects are basically spatial objects located at a precise coordinate. So these might be things like, I'm gonna scroll down a bit, trees. So I think someone plotted every single tree in London, Ontario in this example. And it could also be something like light poles, right? All the light poles within a certain area in London, Ontario. Spatial data can also be represented as lines or be in a line format. And these might be things like streets or rail tracks. So these green lines that you see here, I think represent bike paths or like multi-purpose roads. Okay, and then we also have polygons, and polygons are spatial objects representing an area. So these could be things like a park or a building or, you know, the boundaries of the city of Ottawa, for example. So let me scroll down to see if I can find an example. Okay, so like maybe you're able to see like the red triangles. So those would each be polygons. And there's no example here, but there's also things called multi-polygons, and you can think of them as a collection of multiple separate polygons. So like island chains are supposedly a good example of this. If you think of places like Hawaii could theoretically be represented as a multi-polygon. Okay, so enough yapping, we're gonna go back to our code. Okay, to plot the major rivers running through the city, do you think it's best to retrieve the data in the point format, line format, or the polygon, multi-polygon format that we got from our query.
I feel like lines would be simpler.
Look.
But like, could you not do polygons for more detailed?
Like a
boundary?
fill in.
Yeah.
Yeah, so since we're interested in filling in the blue component of our map, we're going to be selecting the multi-polygon geometry. And there was a bit of trial and error that I had to go through to figure out exactly which which data format was appropriate here. It ended up being multi-polygon, and like allegedly, many large rivers are stored as multi-polygons in OSM. So I guess this is just kind of like, you know, something that you get familiar with as you dig deeper. But yeah, so we're gonna go with multi-polygons. All right, so one, since we have water underscore A defined, let's just try plotting what the multi-polygon looks like. Okay. So I'm just going to scroll down, or you can use the table of contents on the side and jump to step 6. Okay, so I'm going to start. Oh, and we're going to be using ggplot. Back to ggplot. To plot spatial data, we are going to be using geom underscore SF. Okay, and then, sorry, to the data argument, I'm going to be passing water underscore A, which is the object that we defined. And then we're going to be grabbing the OSM multi-polygons attribute. And then I want the fill to be the shade of blue that I've defined using the hex code up here. And I did that just from basically grabbing the hex codes from the preview on the Mark Your Moment website. And I don't want any like gray or black outlines around my polygon. So I'm gonna set my color to NA. Okay, and I'm just gonna run that to kind of show you what I get. Okay. All right. Does anyone want to take a stab at explaining what's happening here?
We have the rivers.
Yeah, we do have the rivers, but it looks like the Rideau River, which is the one down here, extends well beyond Ottawa, way past the suburbs, and even out towards Smith Falls, I think, down here. And you're like, wait, but I thought I defined a bounding box. What's going on? Okay, so I think this is happening because Overpass doesn't trim features by default, and it's going to return the entire feature if any part of it overlaps with your bounding box. So because you had parts of the Rideau River that fell within our bounding box, it's giving us the entire Rideau River back in our result. Does that make sense as to why we're seeing this? Yeah, okay. I see some nods. Okay, so basically, we don't really want this. We don't want to be including all the communities in our print. So to plot only the portion of the river that falls within our area of interest, our bounding box, we need to crop the geometry before we pipe it into ggplot. All right, going back. Sorry. So if you can go to step 5. If you're going along. And is anyone on the cloud? Okay. Oh,
I got an error that watercolor, I just ran that.
Yep.
Watercolor is not defined.
okay. If you run the code chunk that's,
Oh, just above it.
do you want to sit beside the other participant who is on the cloud?
Sure.
Just because there's differences on the cloud. Okay. And I'll get to you guys in a second. Alrighty. Just give me 1 second to situate. All right, so yeah, basically in order to fix our plot, what we need to do is crop our data. So the first thing that we're gonna do is call the stBbox function, pass our bounding box, and use the argument CRS. And the value should be set to 4326.
Are you using Composite Cloud or our studio?
Our studio.
And then we're going to wrap this in another function called st_as sfc. So it should look a little something like this. And basically what this first step is doing is this bit of our code is taking the bounding box that we have and extracting its numeric limits. And then this function, or the function that we have wrapped around it, is converting those numeric bounding box limits into an actual spatial polygon. So spatial operations like cropping can understand what to do with it. Okay. So I'm going to run this. And then to actually crop the major rivers, what we're going to do is call stcrop, pass the multi-polygons that we want to crop, followed by bbox sf that we just defined above. And then I'm going to store this in a variable called water_a_cropped.
What ST means?
st, st, hold on.
Just for understanding.
T is like, I'm not sure what st stands for, but it's a prefix for many of the sf functions.
Okay.
Yeah.
So for the Composite Cloud part,
Yes.
the only difference is st_bbox instead of, or like, sorry, what was the difference?
Yes. Okay. Sorry. And if you are on Posit Cloud, the fastest way would be to open up the Ottawa Map Complete
Okay.
QMD. And then if you go to step 5, you'll find a little note that says, please use the following code chunk instead of, please use this code chunk instead of this other one. Yeah.
ST stand for spatial and temporal.
Okay, cool.
AI says spatial type, but it used to stand for spatial and temporal, but they changed it. Spatial and temporal. Spatial and temporal.
So I'm gonna run that. And I think you can ignore that warning. And then now that I have water_a_cropped defined, I can go back down to where I'm creating my ggplot. And I can replace the data that I had in there previously with water_a_cropped. And now, when I run it, you should see that it's actually trimmed, clipped to the bounding box I defined. Are the cloud users good? No? Okay. I'm gonna run back there. Do you need a code up? Are you good? You're good. Yeah.
Yeah, so basically you guys need that extra because ST and CRS.
Yeah.
So this, that looks like every step.
Yeah.
Oh, but then you have to replace your thing.
Honestly.
Oh, I know, once I
thought
thought
about
of
it,
it, you don't need to, like, you don't need the null guide.
And I got it specifically with the.
Very good. All right, so we have our water done. Now, basically what we have to do is repeat this workflow for the other features that we want to add. So basically, rinse and repeat, you run a query, you pull out the appropriate geometry type, whether that's points, lines, or polygons, and then you crop it to your bounding box, and then you plot it. So let's do that now for the human-made water features that we have in Ottawa, like Dow's Lake and the Rideau Canal.
That was like Stephen made.
It is, yeah. Yeah. All right, so
Yeah.
I'm going back up to step 4, extract OSM data. Give me 1 second. All right. So as I did with my rivers, I'm going to start with the query, pass in add sorry, pass the query to the function add OSM feature. And this time, the key I'm going to be using is water. And the value I'm going to be passing is a character vector. So I want to retrieve things that are tagged with the value lake, canal, pond, basin, and lock. So yeah, it's great to be in Ottawa because you get to work with values like canal and locks, which I think, not all cities have the pleasure of being able to work with.
How did you decide that you wanted to have those as your values?
I will get to that later. Thanks for that question. Okay, and I'm gonna run that. I'm just gonna scroll up a bit. But I can show you what water B returns. Oh, sorry, my bad. I forgot to include one thing. I have to pass this to OSM data underscore SF. And now when I run water B, I should get something like that. Okay, I'm gonna move on to the next step. So now we're gonna crop the result from the query that we just ran. So this time, or like last time, I'm going to start with the stCrop function. We want to crop the polygon format data this time instead of multi-polygons. And then again, passing our bounding box that is defining how to trim, how to crop our data. And then I'm going to save the result of that to a variable called water B cropped. I'm going to run that.
What does it mean when it says warning attribute variables are assumed to be spatially constant throughout all geometries?
So it's a great question. We can check that during the break. But visually, like when I plot the different components together, it looks okay. So I would like to think that the warning is something trivial.
Yeah.
Yeah. Yeah.
Thanks.
Yeah, and I have it too. Yeah. Okay. And now that you have water underscore B underscore cropped, now we can add a new line. So a new geom underscore SF. This time our data is water B cropped. Yep. We're going to use the same hex code since we're still plotting water. And again, when we're filling in an area blue, I don't want the fill to be outlined in gray or black or whatever. So I'm going to set color equals NA. And now when I zoom out, you should see the canal added to your map. And there's also like little bodies of water that are kind of like an offshoot of the canal appearing on your map that you probably didn't see when you first created your plot. All right, 2 elements done. 2 more to go. Any questions? Are we good for speed? Go faster, go slower? It's good? Okay. I just don't want to leave people behind. All right, so we're done plotting the water, which is cool. So now let's move on to roads. So roads and footpaths are tagged as highway in OSM. And if we go back to our glossary, so going to the highway section, you can see that there's a couple of different types of roads. Highways show up as red, trunk roads show up as orange and whatnot. And you'll notice that these colors actually correspond to what you see on the map. So you see here, like the Queensway is red, the Parkway is orange, and other major roads I think like that's Bronson and maybe Carling are in light orange. And basically like the more busy the road is, the more vibrant and bolder the color is. What we're gonna do today, so going back to our glossary, we're gonna be capturing all the different types of roads under this category, roads. And the second category, link roads, to capture the main road network of Ottawa without overcrowding our map. You know, you could go on and plot alleys and pedestrian-only streets and so on, but you do run the risk of overcrowding your map. So just to keep things simple, we'll plot link roads and roads. Okay, so going back to our code. So again, going back up to step 4. Now I'm going to be working in the code chunk that I've started here, labeled major roads. So again, starting it with my query, passing that into the add OSM feature function. And then we said that the key for all roads and footpaths in OSM is highway. And then we're going to define major roads as anything that has the value motorway, trunk, primary, motorway underscore link, trunk underscore link, and primary underscore link. And again, I'm going to pipe that into OSM data underscore.
You have to explicitly list the values. If you know, you're like, I want all of the highway.
Yeah, so if you want all of the highways, then you don't need to provide that, and I'll just give you back everything that has the key highway.
by default.
Yeah.
Okay.
And I think you can also play around with like regex and things as well. Like if you look in the documentation. Yeah. Yeah. And then I'm gonna run this. All right, and then let's see what roads underscore A return. Yeah, any suggestions on which geometry we use for roads? Points, lines, polygons?
Like lines would be sufficient.
Yeah, lines, yeah. Okay, let's query both the major roads and the minor roads, like first, before we move on to cropping and plotting. So I'm just going to scroll down a little bit and then start working on the query for the minor roads. So again, starting with query, passing that into add OSM feature. Again, our key is going to be highway, and our value this time is going to be secondary, tertiary, unclassified, residential, secondary link, and tertiary link. And again, passing that into OSM data underscore SF. I'm going to run that. And I'll just leave both of these code chunks up here for people to get caught up.
I didn't understand that I'm supposed to say. I feel like every time I have to do it, I'm like, okay, I'm just gonna
And you run this,
repeat the same stuff.
type BLT, that should rest your hair.
Yeah, I don't know. Also,
Were people able to complete their query for their major and minor roads? Yeah, I see some nods. Great. I see someone at the door. They're gone now. Okay. Oh. It might be next door. I think there's other meetups happening in the building as well.
Oh, okay, it's for, something.
Yeah.
Sorry.
All right, so I'm gonna assume that you have roads A and roads B defined. We're gonna scroll down, and then we're gonna crop roads A. Oh, sorry, the line format data returned in rows A and rows B, as we have done with the water component. Okay, so again, SD crop. And here, just be careful of which attribute you're grabbing. Oops, so something like that. Sorry. To crop both to crop the line format data returned in our roads A and roads B query. So note that the format is exactly the same, right? Wrapping it in SD crop and then supplying BB box SF as your second argument. And now that I've cropped it, I can continue to build on my existing ggplot. And again, very similar patterns here, right? We're going to use geom_sf. The data that we're going to provide here is roads A crop. And since we're dealing with lines instead of like a fill, I'm going to use the color argument to specify what color I want the roads to be. So I have a couple of hex codes predefined here. So I'm going to use roads A color for that black. And you can play around with this yourself, but I want to make the line just a little skinnier than the default and just a little less opaque than the default. So I'm supplying an alpha value of slightly below 1. Sorry. Something like that. And then I can add to do the same thing for roads B cropped. So I have a different color defined for minor roads. And since they're minor, I want the lines to be more thin than what I have for my major roads. So maybe I'll supply a value like 0.5. And then I'd want these lines to be even more transparent than the lines that we have for the major roads. So something like that. Gonna run that. And then you should start getting something that resembles Ottawa more or less. Okay, so I'm just gonna scroll back up a little bit while I wait for people to get caught up. And then yeah, we just have to plot our greenery and we're almost done. All right, so we're like 75–80% of the way there. So let's finish this off. All right, so just going back to our demo, or like what we're working off of. When I looked at this map, it kind of looked like there were 2 shades of green. One, it's a little harder to tell on this big screen, but yeah, some greenery looked lighter than the others. And I tried to figure out if there was like a rhyme or reason to it, but really couldn't. So for our plot, we're just going to take a simpler approach where we're going to use 1 shade of green for natural greenery and then another shade of green for more human-made stuff. Okay, so going back to our studio, again, starting back at step 4, now I'm going to scroll down to the code chunk titled natural vegetation. So we'll start off with that one. Give me a second. All right, so again, starting with a query, passing that to add OSM feature. The key we're going to use here is natural. And then for value, we're going to pass a character string, a character vector with the strings wood, grassland, and scrub. And again, piping that into OSM data SF to retrieve it in the data format that we're interested in. And I'm just going to run that. I'll leave the code up so you can type along. And then if you're a faster typer and you want to start creating the query for the recreational greenery with me, we can do that together. So again, starting with the query, passing that into add OSM feature. Oh, actually, we're going to use, I guess it's sister function called add OSM features. So note that it's plural. And then I noticed if you use this feature, what you can do is pass a named list. And what I can do here is, or I guess to explain like when I was using add OSM feature, I could only use one type of key at a time. But if I use add OSM features, I can use multiple combinations of keys and value in one query. So to demonstrate that, basically grass, forest, recreation underscore ground. So I guess the first part of my query, we're looking at things that have a key of land use and a value of either grass, forest, or recreation ground. But then I'm also going to be looking for features that have a key of leisure and has a value of one of playground, park, garden, or dog park. And we're using a different function here, add OSM features, but you can still pass it to the same OSM data SF function to finish everything off. I'm going to run that as well. All right.
I have a question.
Yes.
I don't know if a feature kind of falls into more than one of these, I guess, like keys.
Yeah.
Is it duplicated in the like in the spatial data? Like, is that something you have to account for? So I'm thinking like Jack Purcell is like a park, but also a dog park.
Then it would be, it should be tagged as both.
Okay.
Yeah.
But it only like kind of shows up once in the spatial data that you extract.
Oh, I see. I haven't tried it. I don't think it would duplicate it.
No.
We can try it.
It might just plot over itself. Like if there is a duplicate, it might just, like if there's a park and a dog park, and then when you plot it, it's just probably, maybe it's plotting over itself. Anyway, I was just curious.
Yeah. If your query is looking for either a park or dog park, then that park should only return once. But if you're like querying for parks and then you query for dog parks and then you plot those two things separately, then you would get an overlap in your plot, I think. I can test it out though. Yeah. All right, so hopefully you're done querying for natural vegetation and the recreational greenery in Ottawa. So I'm gonna scroll down. So it's the last bit of cropping we're gonna have to do for today. What did we call it? We called it natural. And for parks, or sorry, for natural greenery, we're gonna be grabbing the OSM polygons. And again, supplying bbox SF. And I'm gonna be calling this natural underscore cropped, just to follow the convention that we've been, following up until this point. And then finally, we're going to be doing applying the same cropping method to our areas of human-made recreational greenery. So I called that rec. And again, I'm going to be grabbing OSM underscore polygons, passing in bbox underscore SF. And then I'm going to store that in a variable called rec underscore cropped. Then I'm just going to run those two lines of code. So now I have natural cropped and rec cropped available in my environment. Then I'm gonna scroll down to step 6, and you can see that I've already defined 2 shades of green. I'm using a darker shade of green to capture the natural greenery, and then a lighter shade of green to capture the recreational green spaces in the city. And then we just have 2 more geom SFs to add to our plot. And one thing I'm going to note here is that when we're layering multiple geomes to create map art, it's very important to think about the order in which we draw the different layers. So I think like as a rule of thumb, it's a good idea to have your water and your greenery layers placed under your roads. Otherwise, large polygons like large parks, maybe large rivers can clip the roads and make it look like the roads don't continue through an area, even though it should. So with that in mind, we have our water layers as our first two layers, let's add our greenery layer in between our water and our road layers. So gonna, oops, my bad. So gonna do data equals natural underscore cropped. Fill is going to be natural color. And again, I don't want like a outline around my parks or like a black outline around my park. So I'm going to set color equals to NA. And then finally, I am going to add rec underscore cropped. I'm using the lighter shade of green here. And again, setting color to NA. So we're not outlining our dog parks and playgrounds and things like that. All right, so I'm just gonna run this to make sure my plot looks good. Okay, so that looks fairly similar to what I have in front of me. I'm just gonna scroll back up. I'll keep the code here for a little bit and I'll just go around the room to make sure everyone's good. Does anyone need help? Okay, okay. Oh, and then sorry, so going back to the question that Brittany had earlier of like, well, how did I settle on the different key value pairs that I'm using to capture the different parts of the city and in particular the greenery in Ottawa. So to show how I did that, at the very bottom of this file, you'll find a commented code chunk that's called how to find which features you can plot. And basically it's like a function and a and a for loop that returns all of the key value pairs for selected keys within a bounding box. Now, I think that what I did is a useful way to explore what features exist and what you can plot, provided you're working in a small area. But then again, like I wouldn't recommend doing this for larger bounding boxes, say for example, like all of Ottawa, because then this query is going to get like way too computationally expensive and you might time out again and again. But basically, yeah, I just asked OSM like, okay, given the keys natural, land use, leisure, water, which I think should capture different elements of greenery in the city, what are the specific values that are used within this particular area of Ottawa I'm looking at? So yeah, lots of trial in there. Yeah, yeah. Sorry, I'm just gonna jump up. Okay, so yeah, we just have to add a couple more bells and whistles to our ggplot, and then we're done. I see a hand. I'm gonna. Oh, yeah.
Earlier, like I had asked a question if you can, in the like get baby function, if you can put like arbitrary things and you can.
Okay, cool.
So the reason it wasn't working for me was like a separate thing entirely.
Okay.
So like I can type, for example, like Trent University in the get BB function and it like finds the bounding blocks.
Yeah. Cool. All right, so I think I'm just gonna touch up my ggplot and then yeah, we can continue moving moving forward here. This plot looks good, but you can still see things like this margin we probably don't need, and also this like gray and white background with the major and or minor grid line. So those are components that we want to remove before we head into our printing phase. So a couple of functions we can layer on to our ggplot are coord underscore sf expand equals false. And what this is going to do is remove our margins. Or sorry, I guess like the padding that was there around the plot. So you can see that's gone now. So our map looks a little crisper. And another thing I'm going to do is to apply the void theme. And you can see that removed the axis ticks and labels, and it also removed the major and or minor grid lines that I had in the background of my plot. So now so basically now everything that I didn't explicitly fill or draw using my OSM data is kind of filled in using this shade of white But if I want to, if I find that this white is a little too like cool toned for me, like it doesn't really go with the rest of the colors that I picked, how I can change this is by manually changing the panel background color. And I'm going to use the element underscore rect function and pass this predefined color to the fill argument. And I've predefined this color in the code chunk above, as I have done with the other parts of the map. So now when I run this, yeah, you basically have what I have in front of me in that frame.
Lighter. Is it just the printing?
Maybe. So I'm just going to quickly explain how I added the text, and then we're, basically done with this map. So I'm going to save or store the result of that in a variable called plot. Okay. And then we're going to work on, this last section. I'm just going to uncomment this. And let's just quickly define a color palette that we're going to use to fine tune how we want our print to look like. So I want the background of my print to be white. So I'm just going to use pound FF. That's the hex code for white, or I think you could even just do white in quotes and that might work as well. And then for text, I want it to be black. So I'm going to do pound 000000, which is the hex code for black. The city that I've plotted is Ottawa. It's in Canada. And then its coordinates are 45.422. Ooh, I don't know how to do the degrees. I'm just going to do N for now. 75.699 W. All right. So I have some of the parameters set up to control how I want my print to look like. So just a little commentary on viewports. So in this final code chunk here, you can see that I'm using this function from Grid, I believe, called viewports to precisely control where each element is positioned on the final print. So this includes things like the map and the text. So the details of like how grid and viewports work, I think is like outside the main scope of this workshop. So I'm not going to dive too much into it. But I'll just walk through the code that basically takes these city and country names that we've defined in addition to its coordinates, how it arranges everything, and then exports the final image as a PNG. So the main takeaways of this code chunk in front of me here is that we're creating a separate viewport for each of the 5 elements on our print. So the 5 elements are the background of the print, the map, the city name, country name, and coordinates. So if you look at this code chunk, you'll notice that I've created 5 viewports using 5 distinct viewport calls. And another thing to note here is that I'm using the show text function, functions from show text and functions from sysfonts to use Google Fonts in R just so that our final output matches the design style that we're aiming for, since we're unable to do that using just the default fonts available in R. Yeah, and then if you run this code chunk, you should get an image called ottawa-map.png saved in your project directory that is based off of the plot that you created over the last hour and a half.